Very good morning, everyone. Can you guys hear me? Let me know in the chat. Very good morning, Manoj. How you guys are doing? You guys had break on Friday. So how was your day, guys? Very good morning, Ekta. So today actually I'm in very new place in Ghaziabad. So I'm just apologizing in the starting. You guys might hear some voices or you might see some people also to coming here and there. So sorry for that in starting, guys. Yeah. So yeah, apart from that, yeah, actually it can happen, right? I'm not at my regular place, so things could be different here. Might be some internet problem can also happen, but I have made sure that that internet is already good here, like near to 47, 48 MB per second. So we should not face any network problem. But yeah, some background noises can come. So just bear with it. Yeah, it will happen just for today or next class. Okay, guys. So how was you guys doing on Friday? Have you tried to solve any of the problems? See some background noise already. I'm hearing here. Very good morning, Arad. So you guys have practiced any of the problem on Friday, or like started solving the questions which we from the lead code? Because I think we have already covered stack and queues and all the important data structures. So I'm believing like everyone now start looking into the lead code problems. Great. Anyone was facing any problem while trying to understand the last class problems? We can talk about that as well. Water.js. What is this? Is it the problem you're talking about? Water.js? What is this, Arad? Oh, we have the problem water.js. Okay, let me check. 1 minute. Let me first share the screen. There is no code there in repo. Again, I left an even problem. I believe I don't remember any question related to water.js. I mean, check that in repo. Okay, 1 minute. Water.js. So it should be in sorting folder, right? Oh, stack. Okay. Oh, water.js. Okay. Hydro was you need to find the max volume of water that can be stored between the whenever it rains. Oh, okay. So yeah, this problem solution we have not written here. Oh, I think this one is here. Rain trapping one. So we can delete the file of butter.js. I think we have the solution there in the rain trapping one. They both are same, right? Let's see. Height of walls, you need to find the max volume. Yeah, this one we can delete. Okay, Arat? Rain trapping is there. We can delete this file. Yeah. So no worry on that. Yeah. So today's problem, guys, which we are going to discuss. So today's topic is advanced problem on searching, right? So if you guys remember about the searching scenario, so what is the first thing which comes into your mind? Like the first topic where we started talking about searching. Anyone wants to think about it? What is the first thing which we looked into when we talk about the search scenarios? Linear search. Great. Any other techniques or any other thing which is coming into your mind while we are trying to search something? Binary search. Yes. say linear search and the binary search. So most of the time we say that linear search is the bootstrap, or the initial thought, or brute force, sorry, not bootstrap, brute force approach. We say that the linear when we look for any of the elements in array in a linear approach, we say that it's a brute force approach, where we are going to look into each of the elements in array, and then we are saying that this element exists in array or not. Correct? That was the linear approach, linear search, where we do that. We also say that as a brute force approach. Correct? Where we just run loops, and in that loops we simply check that we just like traverse all the element exists in that array, and we find it out that element exists or not. Correct? That was the linear search approach. The another was the binary search approach, right? So in the binary search, if you guys remember about it, the first condition for binary search was, you guys tell me, what was the first condition which binary search asked or required? Yes, the array should be sorted. This is the first condition which binary search says to you. Correct? So now once your array is sorted, so it means you have something like incremented all the elements in incremented pattern, or all the elements in the decremented pattern, right? So when you have the elements in your incremented or in the decremented pattern, so you can easily find out a lot of things like min or max. Easily you can find out min or max, right? Because if you are following the incremented pattern, right? So always the first element in the array would be your min element, all, and last element in the array will always be your max element. So that's called the incremented that's called the when we sort your array, so you can easily find out min or max with just the constant time complexity. You can see there is nothing there, you already know the places of those elements, you can easily fetch them. Same when you have a sorted array, and when somebody is saying to you, find out this element exists in array or not. This element, simply they're saying that the question could be, find out this element exists in the sorted array, or find out the index of this element exists in the sorted array or not. These are the questions people will ask. If you will do the linear search, the time complexity would be O of n here, because what you will do, you will check each element in the array, and then you will check compare the values what you are looking for, whatever your target is, you will compare it. But in the case of binary search, what happened, we, because our array is sorted, so we first find out the mid element. Correct? Once we find out the mid element, now we know that the left side of the mid element will always be smallest element, and the right side of that mid will always be greater element, right guys? So now we know that when we are at the mid place, we can easily first compare our mid with the target value. Compare our mid with the target value. If mid is, if the value of mid is greater than the target, if the value of mid is greater than the target, it means now we need to look into the left side, because our array mid is greater. Guys, array mid is greater than our target. It means the value will be on which side? Left side. So we need to decrease our search space now. Rather than looking into whole array, we will just look into the half of the array. Again we'll do the same thing. Again we find out the mid element in this the sorted, like the left side sub array. Well, again we'll find out the mid element. Again we'll check the same thing, is our array of mid greater or smaller. Based on that, we will simply reduce the search space. And then guys, rather than traversing whole array, we can easily find out the element in log n complexity. That's why binary search is very nice approach, and lot of places we use the binary search. I hope everyone remember about the binary search, guys. Anyone has any queries on binary search and linear search? Let me know in the chat right now. No? Yes? We have solved a lot of problems. I remember, we have discussed very nicely, like very deep also about the binary search. And then we jump into a lot of, then we just solve a lot of problem also with the help of binary search. Do you guys remember? like the cow aggregation problem, sorry, not aggregation, cow aggression problems, and like there was books, something related to books problem, or painter, yes, book allocation, and painter allocations, and I remember a lot of problem. I think I have very good problems we have solved with the help of binary search, right guys? Search in rotated sorted array. Yes, search in rotated search sorted array. Today also we have one question actually in the rotated search array, rotated sorted array. So we'll see that question also. Yeah, median question also we have solved. Yes, remember the median question was also very tough question, which we looked into. Median question was very tough question also. I remember when we have two sorted arrays and we find out the median. I remember that question. So those are very nice questions. If see, those are not easy questions. First thing, but yes, if you will spend some of the time to understand the logic of those questions, I think you will guys feel very happy and confident after solving this problem with the help of binary search. Okay, guys. So that's all about binary search or simple searching. Want to talk about? See, yeah. Apart from arrays, I remember the searching could apply in uh, any of data structure, even in the stack or in the queue, right, guys? There could be some problem where they are saying that can this element exist in the stack or can this element exist in the queue, right? Or similar way, can this element exist in the linked list, or can this element exist in the tree, right? So if somebody was asking about looking for any element in the tree, so what are the approaches we will follow here? Like if somebody is asking, they have given you one binary tree and they're saying that, can you tell me in this binary tree element or node 7 exists or not? So what is the strategies you guys will use? I'm talking about the binary tree, guys. Binary trees. What are the strategies you guys will use? Anyone wants to think about it? Acha, okay. Before that, tell me, what would be easy? What would take less time? In the search tree or in the binary tree? Okay, answer me this first. Where it would be easy or it would take less time? Searching in the binary tree or searching in the binary search tree? Okay, Aras says binary, Ekta says binary search tree. What about the others? Guys, you guys will speak, then it would be great, right? It can be good collaboration between each of us. I remember like earlier, one more person has spoken. Manoj was there. Deepak is here. Sasan is here. Suraj is here. What happened, guys? Is it little early for you guys? That's why you guys still feeling sleepy. We are just right now not. I am not started anything new. I'm just talking about whatever we have discussed in our previous classes, right, guys? So my question is right now. Let me repeat my question again. Okay, for everyone. So my question is, guys, which would be easy or take less time if we are going to search in binary tree or in binary search tree? Which would take less time to search? You guys tell me which would take less time to search. Arad now says BST. Ekta also says BST. What about others? I'm waiting for others to answer. Suraj is there. I remember. I can see the Suraj there. Deepak is there. Manoj is there. Joseph has joined. No problem, Arad. So, guys, what happened? Okay, so Joseph want me to repeat the question. So Joseph, my question is that where would it take less time or it would be easy to search any element in the BST or in the binary tree? Where it would be easy or take less time? Search for any element. Is it in the BST or in the BT binary tree? Deepak says BST. Thank you, Deepak, for responding. Says BST also. What about others? Manoj, Suraj, Sasan. What do you guys think about it? Okay, I think they are facing some network problem. I'm not sure what happened, but yeah. So I think yes, that's guys. Your answer is totally correct. Navneet is also there. Okay, yes. Thank you. I have not seen the Navneet. Okay, great, Navneet. Yes, it's BST. Yes, definitely, guys. It's a binary search tree, right? Why it would be easy? Because the binary search tree has a specific property, and that property is the left child will always be less than the root one. Left child node will always be less than the root node, and right child node will always be greater or equal to the root node. That's why when you're finding out any element, you can easily ignore the one side of you can easily ignore one side of tree. Same like we are doing in the sorted array. Same you will do in the BST also. But in the binary tree, it would be difficult because binary tree does not have any conditions like that. Binary tree says that you can have max two childs, right? So that element can happen on any side. So that's why. Okay, now let's come back to the question. First question, in the binary tree, if you want to search any element, what would be your strategy? Because in the binary search tree, we are clear that we will compare the value. We'll compare the value with the root node, and based on that, we will go into the left side or right side, right? But what would be our strategy to search any element in a binary tree? What do you guys think about? If you want to search an element in the binary tree, what would be our strategy here? Okay, let me break this question a little bit more, right? So, for in a binary tree, as we know that we have two ways, right? One is through BFS and another one is DFS. Correct, guys? So now you guys tell me which approach you will take here while searching any element in binary tree. Now, does this make sense now? BFS. So Joseph says BFS. What about others? What about others? Deepak, Arad, Ekta. What do you guys think? Arad also says BFS. Deepak also says BFS. That is totally right, guys. Because BFS will make more sense compared to DFS. Because in the BFS, we are going into the breadth wise, right? So if any element is going to be in left side or in the right side, we can directly search there. But if we will go into the DFS side, so what DFS says? Go deeply in one side, go deeply at one side, then go for the another side, right? So BFS, in the BFS, at one iterations, we can check for the left side as well, and as well the right side, correct? But in the DFS, we have to go deeply into one side, then we can come back and look for the another label, another child of that, another side of it. So that's why, guys, it would make more sense to use the BFS here. So Ekta says DFS. So Ekta, DFS will not make more sense here. No, no, no. It will be BFS, which would make our search easy. Because in the BFS, let me draw that. 1 minute, guys. Let me come back to OneNote and let me draw that. Let me draw that. So this is our binary tree, guys. So binary tree, what condition it has? It should have all at most two childrens, right? So let's create that. Right? Is this binary tree or not? Guys, let me in the tell me in the chat. Oh yes, I was talking about binary tree. Yes, yes, guys. Oh, understood. Okay. Oh yeah. So see, guys. Now, if you want to look for that node six exists in this binary tree or not, now if you follow the DFS approach, right? So how the DFS will work? DFS has three approaches, right? Pre, in, and post. Right? We have three approaches for DFS: pre-order traversal, in-order traversal, and post-order traversal. So in each of the traversal, we directly go into one side of a tree, right? One side of a tree, and then we explore all the nodes in the one side. Then we go into the next side of a tree. Then we explore all the nodes into that side. Am I right, guys? That's how the DFS work. That's how the DFS work, right? We explore we explore deeply into one side, and then we come back to the root node, and then we go into the another side of it. That's what the DFS means. But let's talk about the BFS. Let's talk about the BFS. I'm not saying, guys, that BFS will always be most suitable answer here, but most of the scenario, like 80 to 90%, BFS will give you more better results compared to DFS, right? So see, guys, now in the BFS, what we do in the BFS, in the same diagram, if we talk about the BFS, so we start by on the label wise, right? We start searching on the level wise. So there are a lot of chances we can get directly result here rather than exploring these last node. But I'm not saying, like, guys, why the BFS will always be perfect answer, because see, if we are looking for 10 element 10, right? So you can see in the BFS also we have to traverse all of the nodes, or but yes, pre-order, in order, post, it would be equal to it, or like all most of the scenarios, BFS or level order traversal will be equal to pre and post, and like DFS can give you result most of the time equal to BFS, but there are many scenarios where BFS can give you more better results compared to DFS. So that's why we will use BFS while searching any element in a binary trees. Does it make sense now, guys, for everyone, why BFS would make more sense here rather than DFS? Yes, for everyone? For everyone? Okay. So now after that, I think let's see what other data structure we have talked about. I think after that we talked about our hash table. So in the hash table, I think searching is very easy, right, guys? So just quickly tell me why it is easy in the hash table. Why searching is very. Just see. Let's skip next topic. How quickly I shifted to next topic. Your thoughts should always be not you. Priority queue is heap. Navneet, priority queues are heap, max and min heap. We'll talk about them as well. But right now I'm talking about the hash table. That object and map, right, guys? In JavaScript, we say hash table and map. So I'm talking about right now the hash table. So why it is very search in hash table? Yes, because the purpose of hash table is the to make your search constant. Purpose of hash table is make your search time complex. Search time constant. And why? How they do it? They use one hash function for that. Whatever data you are providing, is string, number, anything, they will convert with the help of hash functions. They will provide you one string or one some key. In one way, we can say that they will provide you one key or index, which that index will tell you where this particular data has been stored. So you quickly search for that index, and in the constant time you can get back the results. That's why you do not need to do any traversing there. You just need to do computation, like the calculation of hash value. It's a computation, not the traversing part. And then quickly you will get the keys. You will look into the array or wherever you want to look. You can get back the. So that was the I think we do not see the purpose of heap or priority queue. It does not serve the purpose of searching element. It does it does the purpose of element. Right now, me. So it does the purpose, does the purpose of finding out the min and max values. And the anyone facing audio is stuck? Can you guys not hear me? Okay, let me refresh it. Can you guys hear me now? So guys, not a problem. So guys, again, I'm telling you, I think I already told you in while starting the class, I'm at my very new place. I already checked the internet here. It should be have good connectivity. So, but still, if you guys any problem, so I'm just apologizing. I think you guys can hear some backgrounds as well. So sorry for all that. Is it happening again? Okay. Okay, let me check the internet. 1 minute. 1 minute. Now fine, huh? See, the internet speed, downloading speed is coming to 43 here. And upload speed is less. So the uploading speed is less. No, mic problem can't happen. Might be due to uploading problem, it's not able to upload the live data into some system. Okay, I will continuously check here and use the browser so you guys can continuously hear me. Okay, so did you guys understood the last part where I was talking about the min heap or max heap and the priority queue thing? Do you guys understood? Yes. So that's all about the theory, guys. Now let's jump into our today's question. I didn't come to chat here, understand it or not. So there not be any problem into that. Okay. And sorry for that again, guys, if you are hearing some background noises or having some internet connectivity problem. Yeah. So let's jump into our today's first question, guys, and let's solve it together. Okay. In meanwhile, you guys can just let me know you guys are able to hear me or not. Okay. Okay, so now let's open the first problem of today and let's look into that one. You guys are able to see my screen? Yes, okay, great. So the first one is, guys, you find that of a binary. So they give us one unit. They will be giving us the root of that binary tree and the maximum depth of the binary tree. So before jumping into that, guys, you guys tell me, because I already told you how to find out a depth of a binary tree. How to find out the depth of a binary tree? What's the definition for that? Finding out the depth of a binary tree or any node. No, just not root that node. If I'm talking about, if I'm talking about depth of a binary tree, so you have to tell me the exact definition, not root node. The distance between leaf node to that node. That's also not correct. Please correct your definitions, guys. From that node to leaf node, no. Leaf anywhere. Number of edges, no. No. Definition is not correct. Definition is from the root till the leaf. What do you think? Is stuck in? Okay, let me try that. If that can happen, I can close my video. Let me check. I don't think, guys, I can disable the video or anything like that. There's not an option like that. Okay, I'm not sure is there any option like that. So, guys, what I was saying, the definition for the max, like finding out the depth of a binary tree is that from the root node till the farthest leaf node, not the leaf node only, till the farthest leaf node, that would be the max depth or depth of a binary tree. Correct, guys? Not the leaf node. That's what you guys are facing the problem in the definition. Okay. Did you again facing same audio and video problem? Root node. I'm talking about the depth of a binary tree, not any root node, not any specific node. So when we're talking about the root, when we so you guys are able to hear me, right? Just ignore the video. Just ignore the video. You guys are able to hear me or not? Yes. Okay. Great. So, so guys, the definition of a depth of a binary tree is, yeah, so definition of a binary tree is, you can see maximum depth of a binary tree is the number of nodes along the longest path from the root node to the farthest leaf node. So in your definition, you guys were missing the word the farthest leaf node. That was the problem actually in your definition. Otherwise, your definition was totally correct. From root node, you guys were telling the definition from root node to leaf node. You just need to add from root node to the farthest leaf node. That would tell us the definition. That will give us the depth of a binary tree. Understood, everyone? Let me show you the example also. Just guys creating a binary tree here. Okay. Now, guys, tell me what would be the depth of this binary tree? Depth of binary tree. Guys, tell me the depth of binary tree here. Tree. Right, guys? So how you have identify? Because see, according to your definition, this could also be the leaf node. Right, guys? This could also be the leaf node. This could also be the leaf node. But no. But no, right? You are looking for the farthest leaf node. Yes, and the farthest leaf node is this one. So that's why, and you have to just count. You can see the depth would be here. You can see root like how many nodes are between that. So 1, 2, 3, and 4. So depth would be 4 here. Or you can, if you are starting from 0, if you are starting from the 0, then depth would be 3 here. If you are starting with 0, if you are considering this is a 0, 1, 2, and 3. But it has to be in its path, right? For example, for node 5, it would be 1, right? For node 5. No. Yes, it has to be in the root. It has to be in the path. It has to be in the path. Yes, it has to be in the path. So that's the meaning of, right, root node to the farthest leaf. Root node to the farthest leaf. That's why the definition is root node to the farthest leaf. So from any node from where you are checking the depth, from that node to the farthest leaf. Understood, Ekta? From that node to the farthest leaf. It means the path has to go from that node to the farthest leaf. Okay, that was the definition of hair. And now we have to solve, we have to calculate the max depth of a binary tree. That's what the question is giving to us. Now everyone has understood the question. Everyone has understood the question. Yes. Okay. Okay. Now let's see how we are going to solve this problem. How can we write the code? Yes, definitely we are going to use the recursion. No doubt into that. Definitely we are going to use the recursion. So let's think about the logic. Okay. Let's start, guys. Let's start from the last node, the leaf node. What would be the depth here? For this node, what would be the depth? And guys, I am considering, no, no, I'm considering it as, I'm considering it. See, what is the definition says? What is definition? Maximum depth of a binary tree is the number of nodes along the longest path. You can see in this example also, 1 minute, 390, and they were asking, yeah, okay, yeah, we can go back example. Nodes in that path, number of nodes in that. So how many number of nodes are there? 1, 10, 6, and 4. So according to that, answer should be 4, guys. The answer should be 4. Understood? They were talking about not of edges. They are not counting out the number of edges. You can see number of edges would be 3 only. 1, 2, and 3. Number of edges would be 3. That is the definition of height. If you guys remember the definition of height, where we count the number of edges. But the depth, we count the number of. Guys, are we clear? The number of nodes and number of edges. So if we are counting out number of nodes, okay, let me try it again. So about from root node to leaf node, you just need to count the number of nodes in that path. That would be our depth. And when you are counting out the edges, that would be our height. That would be our height of a binary tree. That's what I was explaining. Now you understood? Now you see Suraj here. From this node, this is a root node, right? To this last farthest leaf node, you can count out the number of nodes here. 4, 6, 10, 1. So you can see 1, 2, 3, and 4. That's why our depth of a binary tree is 4. Understood, Suraj, now? I was saying here? Yes? Okay. Now let's see if I'm talking about the last node, guys, which is 1 here. The last node. What would be depth here for the last leaf node? What would be the depth for this node, guys? 1, right? The depth node would be 1. So for depth, we count the number of nodes, and or the number of nodes, Hariharan. Number of nodes, not the edges. Number of nodes. Understood, Hariharan? Yeah. Okay, so for this, guys, the depth is 1, right? For this, depth is 1. Now tell me about this node. What would be the depth here? What would depth here? It would be 2, right? That would be 2 here. Okay, what about here, guys? What would be depth here? Depth would be 3 here. Okay, what would be the depth here, guys, for this 9? What would be depth here for 9? For 9, what would be the depth here? It would be 1, right? So it would be 1 here, not 3. Correct, Hariharan, why you are saying 3? Is there any reason for that? Oh, no problem, no problem. Yeah, so depth here would be 1. So guys, now let's observe something here. Now let's observe something here. Oh, I counted from the root. No, no, no. Just count for that node. Just count from that node. I'm not talking about the root of node. Say, how are you calculating here? How this is 2 now? You have to calculate from the 1 minute, guys. Oh, yes, that's right, guys. Yes, yes, 1 only, correct. Correct. From that node, you have to check the leaf node, not from the root node. Yes, Joseph. Yes, Joseph. That's what we are doing. From that node, you need to count the farthest leaf node. And you can see from for 9, there is no farthest node. So that's why it would be 1. Am I right, guys? Are you able to understand? Yes, Joseph, did you? Yeah, okay, great. Let's move further. So now, guys, let's observe something here. If I want to find out the depth of this particular node, 6. So can you see some of the observation? Can we see some observation here? So you can see here, for its right node, from its right child, the depth is coming as a 2. Or from its left side, depth is coming as a 1. So can you see that first we are selecting for this node, we are selecting max of its right or left, max of its right child and left child, and then we are doing plus 1 on that. So what I'm doing, max of left child, comma right child, plus 1. Am I right, guys, or not? Can you make this observation or not? Can you make this observation or not? From the left side, whatever depth is coming, and from the right side, whatever depth is coming, you need to take the maximum of both, and then you need to do plus 1 on that. Are we doing it or not? Can you observe it? Just for note 6. Just for note 6. Just observe for note 6. Yes, everyone agree on that? Why plus 1? You get the left is 1 and the right side is 2, and then we did plus 1, then only we got 3, right? Hariran? That's what the observation is. Then we did the plus 1, then we only get 3, right? Correct. Now you understood? Plus 1. Now let's look for is the same uh, logic applying to 10. Let's look for 10. So from the left side, it is coming as a 1. From the right side, nothing is coming. So we'll take it as a 0. Take it as 0. And then we will apply the same thing. Max of left side is 1. From right side, nothing is coming. We'll consider it as 0. So max of 0, 1 is 1. And then we're doing plus 1. That's why we are getting that is 2. That's why we are getting depth as a 2. Same apply here also. For 1, we do not anything from the left side. So it means 0. We do not have anything from the left, max of left side, because it's both sides 0 0, so it would be 0 plus 1. That's why we are getting this one. Guys, can just observe it now. Can you see that everywhere we are just applying this logic or not? Max of left side, max of left and right side, plus 1 on that. Let me know in the chat. Can everyone see that logic? Yes. Yes. Suraj, what about you? Ekta also says yes. Navneet also says yes. Deepak, are you still in the call? Suraj also says yes. So guys, that's what the logic we are right into our, that's what the logic we are going to write in our recursion. So you can see that our base condition would be when we do not have any root. When we do not have any root, just simply return 0. Because you can see for root node 1, we do not have anything on the left side. We do not have anything on the root side, right side. So just return 0 from there. And when you have left and right, when you have left and right, just apply this formula. Just apply this formula. Can we see that, guys? That we just need two things to do here. Whenever we do not have any root, whenever we do not have any root node, just return 0 from there. And when you find out left and right child, you just need to do max of right and left and right plus 1 on that. If we have only root. So Hariharan, you tell me what will happen then if you only have one root. So what will left will return? Because it does not have any left child, so it will return 0. It does not have any right child, it will return 0. So 0, not null, not null, not null. If it does not have any child, it means left will return 0, right will return 0. See, the first thing, what is that? This is it. If root is null, root means child, these child. If these nodes are null, wait, no, do not write it as a node, write it as a node. If node is null, return 0. If node is if there is no node, just return 0 from there. So if we do not have left or right, it means we will return 0 from there. Right, guys? And then we'll apply our logic, max of left and right, which would be, in the case of 0, it would be 0, and then we'll add plus 1 on that. Okay? So guys, first just think about it. Yes, plus 1 will add. Are we clear in our mind how to calculate the depth here? Can we visualize it? Everyone, I want you guys to see every scenarios here. Are we missing any of the scenarios, any of the thing? Can you guys visualize it? Yes, Deepak, definitely it's easy. Deepak was saying somewhere it's easy. Correct. So now everyone has now able to visualize it. Can we move into the code now? Yes. So now let's move into our code. And let me show you, this is a very easy code. So this is all the, see, you will see the below code is just for the binary search tree thing here. This is just for the binary search tree. Okay. Now you can see here the max depth function here. The max depth function here. You can see internally I'm calling, internally I've created one more function as a dive function. And in the dive function, I'm passing my root of the node, right? And then you can see if there is no node, means on the left side or right side, if there is no node, simply return 0. And then count in the else part, if node exists, if any node exists there, so go for the left side, go for the right side, find out the max of that, and then do the plus 1. Whatever I told you outside in the while visualizing, same thing is written in the code. So just you guys can spend some minutes here to understand anything is you guys stuck anywhere in any of the line, then we can go into the next question. Just look into this code. Are you guys facing any problem in this one? You can see simply I'm diving into the left side first, then diving into the right side. Then once we fully dived it out, then we are just finding out the max of it. Then we are doing plus 1. And this is our base condition. While diving left side or right side, anywhere we find out node does not exist, simply return 0 from there. If node exists, go for the left side, go for the right side. Are we good here, guys? Now I'm coming back to chat. Is it easy, right? Everyone can understand it. Everyone can write this code. Yeah. Single node code where? What would be the single node code? What will happen? Suraj, do not think about that. Think about what will happen. What are you doing here? If you have a single node, if you have any node, not the single node, if you have any node, what are you doing here in this code? If you have any node, what are you doing here, Suraj? You tell me. If you have any node, you are going into its left and right every time. Right. So you will return 0 in both scenarios, and 0, 0 plus 1. Right, Suraj? So visualize. Do not see the code. Visualize it. If you have a single node, what you will do, Suraj? You will go into its left side. You will go into the right side, but you do not have anything. So you will return 0 from there. So that's happening. This is code for it. If you have, you will left, you will go into its right, but not have any left and right. You will return both places 0, 0. So 0, 0 plus 1. It was. Yeah, clear? No. That's why visualization is important. That's why, see, now we are at the ending of tools. So we should be good in visualization. If we are not able to good in the writing code, that's okay. But we should be good in the visualization now. Yeah. So anyone have any doubt? We can jump into the code part again. No problem. Or we can clear if you guys have any doubt. Just think about, guys. Okay. Only one node means the depth is 1. If there is no, that's 0. Yes, if there is no node, that would be 0. So that would be the first condition. If there is no node, just return the 0 from there. Yeah. Okay. Joseph, I am not seeing your response. Are you still in the class or you have any bad network or anything like that? Suraj has given response or not? Yeah, Suraj has given yes. Okay. Yes. Okay. Clear? Okay. Now let's jump into the next question, guys. Now let's jump into the next question. Find the unique. I will give you one array, guys, to find element that occurs once in the rest of the element appear twice. So let me come back to now one node. Let's take the same example there. 3, 4, 1, 5, 4, 2, 3, 2, 1, -1, -1. Okay, guys, they have given us this array of integers. And now they are telling guys, in this array, definitely one element is definitely repeating here. You can see 3 is repeating here, 4 is repeating here. But in this array, there will be one number which would be unique here, which means which is not repeating. In this array, every element would be repeating, but except the just one number. And you need to give that unique number as our result, as our output. So you need to find out the unique number here. Otherwise, all the numbers should be repeating. So let's find out. Let's find out 3 exists in the array. Yes, 3 exists. It means it's not the unique number. Let's look for 4. 4 exists? Yes, 4 exists. Let's look for, does 1 exist? Yes, 1 exists. So it's also not the unique number. Let's look, 5 exists? No, 5 does not exist. So that means 5 is our answer. Let's look for others. 4 already exists. Let's look for 2. Yes, 2 already exists. Let's look for 3. 3 already exists. 1, yeah, 1 already exists. -1 already exists. So that's why, guys, our output is going to be 5. That's what they're saying. Let me come back to chat now. That's what they're saying, guys. In the array, you will definitely have all the repeated number. Then only one number which is not repeating there. Okay. Yes, we can. We have lot of ways to solve this question. No. In this question, only will have one repeating number. There will not be many repeating number. That's what here in the constraint is here. There will only be one repeating number. There will not be any repeated anything like that. Or XOR. Yes. So I know, guys, with the help of hash map or object, we can quickly solve it. I know you guys can do it quickly with the help of hash map, right, guys? I do not need to tell about it. Because we have the next question also where we see the hash map object. But here I'm going to suggest to you one more way, that's XOR way. That Deepak has the idea about it. I think Harin also has the idea about it. But there might be some people who does not have idea about how the XOR can also solve this problem है क्या? Please hear me now. Oh, it's still bad. Not sure, guys, because connectivity is good here, but what could be the reason? Might be the reliable platform is not having good thing. Okay, just ignore your part. No, actually, no, here nobody is using other than me internet right now. So might नेक्स्टली इंटरनेट में प्रॉब्लम हो रही है, वो अपने आप रिफ्रेश हो जा रहा है ब्राउजर. Can you guys hear me now? Okay, let's go till the next time we face this thing. Okay, let's go this time. Okay, let's quickly go into the question. So the question is, who somebody was asking question, right? Suraj, it was Suraj, right? So Suraj, we have been given one array. In that array, all the numbers are repeating. There is only one number which is unique in that array. So we have to just return that number, return that unique number as our output. Now, did you understood the question, Suraj? Let me share the screen as well so I can see you the input as well. Yeah, so you can see, Suraj, this is our input. And in this input array, you can see 5 is the only one which is not repeating, which is the unique number here. Other than that, you can see every number is repeating here. Yeah, I will just pause for 1 minute. You guys can see it here. That the 4 is the one is repeating, 2 is the repeating, 1 is also repeating, -1 is also repeating. It's just the 5 which is not repeating. Clear? Yeah. So I think with the hash map or with the help of object, we can quickly solve it. We just need to find out the frequency and the frequency of each element, and we can at the end we can check the number of the number which have the frequency as 1. Just return the result. Correct? With the help of object and map, we can quickly solve it. But let's try another approach, which is XOR approach. Okay. But before that, let's understand why XOR can help us here. Okay, so first understand what XOR does here. So you know about the bit operators, bitwise operators like AND operator, OR operators, NOT operators. You guys are aware of it, right? Everyone aware of it? AND operator, OR operator, and NOT operator, right, guys? In similar way, we have XOR operator as well, which is the combination they have created there. We did in past. Okay, might be we have done it. So see, guys, yes, I think we have done some problem in the XOR. So see, in the XOR, when we have same digits, like when we have same digits like 1, it will give us result as a 0. Whenever we have same digits, the result is 0. And if bits like 1, 0 and 0, 1, it gives the result as a 1. That's what the XOR does. If in the machine you will pass from the one side 0, like different inputs you will pass from there, you will get the result as a 1. But if you will pass the same input or same bit, then you will get the result as a 0. Now everyone understood what the XOR does. Like, let me show you with the example also. Like this, if I 1, 0, 1, and if we have like 0, 1, 1. So see guys, same digit, or let's take one more here, 0, 0, same bits 1, 1, 0, 0, they will always return 0, 0. Different bits always return 1, 1. That's what the XOR does. Everyone understood the XOR now? Can we jump into the next part of this question? Guys, are you able to hear me? Okay, Joseph is. Guys, understood XOR part? I think you guys is stuck after that, so not able to understand. This is understood or not? Okay, you guys have understood, right? Okay, so now guys, let me tell you two more properties of XOR. Two more properties of XOR, which is if we have a number like a 5, let's calculate the binary value of it, which would be 1, 0, 1, right? The binary value of 5 would be 0, 1, right? If we do the XOR of number, it will always give the 0. If we do the XOR of number, the result is 0. Let me show you. So now again, second input is also as a 5. So 1, 0, 1. You can see guys, 1, 1 will come 0, 0, 0. This is a fact, guys. This is a fact, guys. If it will give you 0, it's a fact. Can you guys see it? Can you guys see it with the example? You just take any number, and if you will do the XOR of it, you will get the result as a 0. Guys, are you able to take it? Are you able to understand this part? The first part of it? Aras says yes. What about others? Okay. Okay. Now this is the first property of it. Let's see the second property of it. If we XOR of any number with 0, if we XOR of any number with 0, we always get the same number. The XOR 0, the 5 XOR 5. Correct, guys? These are two properties which XOR provides you. Which XOR provides you. If you have the same number, you will get the result as 0. If you have, second property is, Arad, if you have any number, if you XOR that number with 0, you will always get the same number back, which is 5. If you will XOR 4 XOR 0, you will get 4 always. This is also fact. 13 XOR 0, you will always get 13. Understood, Arad? So these are two facts. Everyone can remember it. Yes, in last we'll get 5. Everyone can remember these facts of XOR. If we have two numbers, if we have two same number, and if we are doing the XOR in that, we'll always get the 0. And if we are doing XOR of any number with 0, we'll always get the same number. Can we remember these properties always, guys? Okay. If yes, let's move into our question now. How these properties are going to help us to solve this problem? How these properties are going to help us solve this problem? Let's see that. Let's see that. So now guys, let's see our question. So what it is asking in our question? In our question, it is asking we need to find out the unique number. It's asking we need to find out the unique number. So guys, if I do 3 XOR of 4, 3 XOR of 4, we'll get some number like 7. 3 XOR of 4 will give us any random number. It will not give us the properties 1. It will not give us the properties 1. But just think about if we somehow get another 3 here. If we get another 3 here, will the result of wherever we are doing the wherever we are doing the XOR with other number, so 3 and 3 will automatically become 0. Correct guys? 3 and 3 will automatically, the XOR of 3 and 3 will become 0. So because see, the question is saying guys, in this array we have all the duplicate numbers. So when the duplicate number will doing the XOR on duplicate number, all will become 0, right? All will become 0. Am I right or not? In the duplicate number, in the array, we have all the duplicates number. All the duplicates number will make your result as a 0. And at the end, you have only one unique number. That's what the array, that's what our question is saying. In the whole array, you have one unique number and all other are duplicate. So all the duplicate number will make, if you will do the XOR of all the other number, all will make it as a 0. And then at the end, we will do the XOR of unique number with 0. Then we will get back the result as a unique number only. Right guys? So see, let's see. Very good example. Like if we have 1, 1, 2, 2, and 5. So what is unique number here? In this example, what is unique number here? This is 5, right? This is 5. So now, if I start doing XOR from here, so 1 XOR 1, it will give us 0. 0 XOR 2 will give us 2. Correct? Till here. Then 2 XOR 2 will give us again 0. And then 0 XOR 5 will give us 5. So now you can see, once we reach here, we get back our result 5. So what is the meaning? This will become, when we'll do the XOR between these two, they will become 0. When we'll do the XOR of these two, they will again become 0. And then at the end, we'll only get back the 5 as our result. Understood, guys? Was it difficult? That's what your code is only. You have to iterate the array, and every time you need to do the XOR of it. And at the end, you will get back the unique number. Even array is sorted or not, how does it make sense? Even if array is not sorted. Even if array is not sorted. So Joseph has raised a very nice question. Even your array is like this sort. Even your array is like this. Okay, even your array is like this, Joseph. Once you will do 1 XOR 2, you will get some number 3, right? Again, you will do the XOR of it. So it will, again, you can see 1 and 1 again matches. Okay, I think you guys might need to see this. So 1 XOR 2 XOR 1 will give you the same result, which will give you 2 only, which it will give you same result, which 1 XOR 2 like some medium middle result, XOR by 1 will give. This and this will give you the same result. That's why I think Joseph was confused. That's why he asked the array is sorted or not. Understood now, Joseph? It will give you the same result. Okay. So it will give you 1 XOR 2 XOR 1 will also give you 2. Or if you will do 1 XOR 2 and you will get some result like 7, and then you will do, you get 7, and if again you will do the 1, you will get the 2. Whatever the middle result is, we are not aware of the middle result. We're not aware of it. But at the end, once you will do the 1 again, you will get the 2 only. Because 1 and 1 has been already made the 0. Understood, Joseph? It's clear now? Even if it's not the sorted, it will give you the same result. Yes, it gives same result. What if some elements repeated 3 times? If some element is repeated 3 times, it will not give us the correct result. It means the third one is unique. Arad, if like there are 5 which is repeating 3 times, so 5 has been already made 0. So now 0 XOR 5 will give you the result as 5. Understood, Arad? That would be your unique number. Three is equal to 3 is equal to 0, and 3 plus 0 is equal to 3. Yes, it will give you 3. No. It will not. We should have one more 3. We should have one more 3. We should have one more 3 to neglect this result. To neglect this result. 3 times also XOR value 0. 3 times. No. How? Starting 3 and second 3 will become 0 only, right? 3 and 3 will become 0. And then 0 XOR 3 will become 3. 3 is not unique here. That would not be your answer. Okay, guys? 3 will not be your answer. You will return the false. 3 is not the unique. There is no unique item. See, Arad, 3 is not your answer then. Even if in your question, if you have 3 times, it's not your answer. 3 is not your answer. Yeah, it's not. So while you are checking, it should not be your answer. Okay, so now let's look into the code as well. Now you can see this code. Very simple code, right? We are just simply iterating it over. Guys, just see it here. And question clearly says that it is going to repeat twice. Every element is going to repeat twice. So that's why this code will totally work here. You can see very easy code. And in JavaScript, that's how we apply the XOR operation, guys. In JavaScript, that's how we apply the XOR operation. Okay, now I'm coming back to chat now. Yeah, very simple code. Arad, question was very clear that every element is going to repeat twice. Is it clear now? Everyone, it's clear. It's very easy code, right? It's another way to find out the unique element when the other elements are repeating twice. No, it will not happen. Then this code will not work. Joseph, question is very clear. You will only get the twice. Any element can be repeat twice, not thrice. This will not work. Is it clear now, guys? In that case, it will return repeated integer. In that case, it will repeat 3 only. In that case, it will return 3 only. If you have thrice, it's logical, right? It's logical, right? 3 XOR 3 will return 0, and one more 3 will return output, it is 3. Yeah, see the code. Clear now, guys? Easy, yes? Yes, only two duplicates. Yes, Joseph. See, let me show you the question, guys. Find element that occurs once in the array where rest of element appear twice. Yes? Yes, if three duplicates are there, then we should look for other approach. And that's the other approach I'm going to discuss in next problem. You can see we have the next problem, which is going to tell find distinct element in the array. Find distinct element in the array. So they are saying given an integer array nums, return true if any value appears at least twice. At least twice. That's the question you guys are asking. If any value appears at least twice in the array, and return false if every element is distinct. That's the question you guys are asking, right? If there are duplicates or more than two duplicates are there, you have to do that. So then XOR approach will not work there. This problem has only one unique number. Yes, only one unique number. All the rest are repeating twice. Now the next question, guys. Next question, everyone understood? You have to find out if in your array any value is appearing twice, at least appearing twice in the array, and return false if every element is distinct. Like this, 1, 2, 3, 4. If every element is distinct here, return false. If anyone is repeating, you can see 1, 2, 3, 1 here. 1 is repeating here. 1 is repeating here. So you just need to return true. Here you can see 1 is repeating 3 times. So you need to return as output as it true. Everyone understood the question? Yes. Definitely we are going to use the map or object. Yeah. So we'll simply use the map. Like if I take the one example very quickly, I think you guys are aware of this question, but yes, just quickly. 1, 2, 1, 2, 3. So in the map, just simply count the frequency of it. So 1 is coming twice, 2 is also coming twice, 3 is also coming twice. So in the map, any element, any key has a value greater than 1. Any key has a value greater than 1, simply return true. Simply return true. Or you can do what guys, while putting any element in the, do not need to count the frequency also. Guys, do not need to count the frequency also. There is one more easy way. Same in the map. Same in the map. You just start putting elements in the map. So first you will put 1. Just check 1 exists in the map. No, 1 does not exist. Okay. Keep it in the map. Now let's look for 2. 2 exists in the map. No. Let's keep it as it. Keep it in the map. Let's look. 1 exists in the map. Yes, it exists. Just return true from here. No need to count any frequency, anything like that. Return true from here. Correct, guys? Correct? That's how you just need to check into the map. Does that element exist or not? If that element exists in the map, simply return true from there. If that element does not exist, you just need to return the result from there. Let's look into the part of unique element as well. If all the unique are here, so what we will do? Does 1 exist in the map? No. Okay, add it. Does 2 exist in the map? No. Okay, add it. Does 3 exist in the map? No. Okay, add it. Does 4 exist in the map? No. Okay, add it. Can you see that now, guys? You have already treated everything, but there was not any duplicate element. So what you will return here? You will return as an answer as a false. Because you need to find out duplicate elements. Is there any duplicate element exist? If exists, return as a true. If doesn't exist, return false. Everyone understood? I think this was very easy, right? Anyone facing any problems? Very easy, right? Or let me show you the code as well. Let me show you the code as well. I'm not using object map there. I'm using the duplicate there. First duplicate number. Yes, we just need to find out duplicate exists or not. They're not saying that first duplicate or the second duplicate. They're just simply asking if duplicate exists. just return the true from there. If doesn't exist, just return the false. Okay. So now let's quickly see the code. And I'm not using map there. I'm using the object. So let me show you. You can see, guys, this is the object which we have taken, visited number. We are traversing our array, taken the value num, and then we are checking nums. If that number exists, simply return true. If not exists, add it into the map or in the object. Let's quickly see the code, guys. It's easy. Are we good now, guys? Anyone has any doubt, guys? Just let me know in the chat. Or we are good. Object. Yes, we are using object here. You can see line number 19. We are simply using object. Clear for everyone? Good. Can we move to the next question now? Okay, now let's move to the next question. Okay, so the next question is searching in BST. So we are given a BST here, binary search tree, where we have to find the lowest common ancestor, which is LK, of two given nodes from the BST. Correct, guys? So now they have given us one binary search tree, specifically binary search tree. So before moving further into the question, you guys tell me in the chat, what is the properties a BST has? A binary search tree, what is the specific properties it has? Tell me in the chat quickly, guys. And you have to shift your mind that much fast. Till now we were talking about arrays and the map and object. Now you have to quickly switch your mind to trees, on specifically binary search tree. So now tell me, what is the specific properties binary search tree has? So Joseph says 1 and 0, left and right. So Joseph, that's all tree has 1 and 0. Yeah, left should be, yes, Hariharan is saying left should be smaller than root and right should be greater than or equal to root. That's totally right, Hariharan. Suraj saying two child, not only two childs, it's the at most two childs or max two childs, Suraj. Joseph says height difference. Height difference, that was the balance tree, which we have talked in our last class. When we're talking about the balance tree, so then we were saying that the difference between the height of left subtree and right subtree should not be greater than 1. That was the balance tree. Joseph, not this one. This is the binary search tree. That's why I'm saying just quickly run thoughts in your mind and think about what is the specific about binary search tree. I think Hariharan has already answered it, but yes, you guys can also think about it. So Arad says left less than root. Arad has given very technically answer, but yes, that's the right answer. I was thinking about that. No problem. Yeah. But see, you are thinking about that. Now you know that. You can tag it in your mind. You can tag it that thing. That the balance or height difference, it means it's a balance tree, right? You can tag it. Left less than root and root should be greater. No, no, no. Not right. Not right. Joseph, your technical one is not correct here. Root should not be greater. Root right should be greater or equal to root. Okay, Joseph? Yes. What about others? Suraj, what about you? Suraj says two child only. What do you think about here? Deepak, Navneet, not seeing your answers, Navneet. What happened now? Oh, Navneet has says yes earlier. Are you guys, and so yes, are you guys aware of that BST part, guys, which we have talked? Navneet, Deepak, Manoj. Okay, they are busy right now somewhere else or might be facing some problem. So yes, guys, that's what the definition of BST is. In the binary search tree, repeat the question. So Deepak, my question was that what is the specific properties a BST has? How can we identify if somebody is saying to you, you need to implement the BST, or in the question, they are saying that it's a BST tree. So what is the first property which you will check about the BST? That's what I was asking. No. So the see, Deepak, the property is in the BST that the root node, I'm talking about the tree right now. So the root node should be smaller than should be should be the root node, or we can say we can go with the child node as well. So the left child node should always be smaller than the root node. Left child node should be always smaller than the root child node, a root node, and the right child node should always be greater or equal to the root node. That was the property you need to check for the BST. Okay. Yes, left is smaller and right can be greater or equal. If we have duplicate elements, then it would be greater. But in this question, guys, in this question, we are not going to get any of the duplicates element. If we go into the constraint, you can see all node dot values are unique. So there will not be any duplicate elements. So now our condition could be the BST, all the left side should be smaller, all the right side should be greater, because we are going to have all the unique elements. Correct, guys? Correct? Because in this question, they are clearly saying that there is not going to be any duplicate elements. So now our condition could be quickly corrected, and we can say that all the right side elements, all the right side node would be greater. Correct, guys? Give me thumbs up here. Did you guys understood this part? Yeah? Okay, great. So now let's move further into this question. What they are asking in this question? They are asking, guys, you need to find out LCA. You need to find out the LCA. And if you guys remember about, we have already done the similar question. And in that question, I'm not sure you guys remember about it. So the LCA is lowest common ancestor, is a node which is common ancestor to both the nodes here. And the node itself can also be considered as a common ancestor. So now let's draw it in our one node. Let's go back to our one node. Yeah, 6. Let's draw the same code. 2, and you guys can check that it is following the BST properties or not. 0, 4, 3, 5, 7, and 9. So first tell me in the chat, is it following the BST properties? Coming back to chat now. Yes. Everyone says yes. Anyone is seeing it, it's not following it? Correct, guys? Everyone can see that? Yeah. Okay. Now it's a complete also. No. It's not complete binary tree. Okay. Now let's look for LCA, guys, which is lowest common ancestor. Correct, guys? Which is lowest common ancestor. So what is the meaning of lowest common ancestor? So ancestor means that the both nodes should be generated from that parent. Both child nodes should be generated from the parent, or the common node between the nodes. Like, see, in this question they are giving us two nodes here, 2 and 8. So in this question they are giving two nodes, node 2 and 8. They are saying, tell me what is the LCA for these two nodes. So for these two nodes, for node 2, this one, and for node 8, what is the LCA? So LCA is lowest common ancestor. It means the first node which is adding them. The first node which is adding, so which is 6 here. So for that, our answer would be 6. The common node which is going to add all those nodes. That's what the definition of LCA is. You can see the lowest common ancestor is a node which is a common ancestor to both the nodes. Common ancestor to both the nodes. And guys, here the node itself can also be considered as a common ancestor. The meaning of it is, if I am talking about like let's take a example of 4 comma 5. If we want to find out the ancestor of 4 and 5, 4 itself can be the ancestor for 4, and it could be the ancestor of 5 as well. So that's why the LCA here for the node 4 comma 5 would be 4. That's what the LCA is. The node which is the common ancestor for both of the nodes. And in the same case, when we have 4 comma 5, you can see that the node 4 can itself be the ancestor of itself. The node 4 can be the ancestor of itself, and node 4 can also be the ancestor of node 5 as well. Can you see it, guys, everyone? What is the meaning of LCA here? Means root or subroot for those two nodes. Means root or subroot for those two nodes. Hariran, can you repeat your question? So the LCA is the ancestor. Ancestors, like in the family, if we have two brothers, so our parent, our father or mother, this could be our ancestors, right? Right, guys? So those are our ancestors. So that's why they're saying the common node which is generating these both nodes, that person, the first person in the list, will known as the ancestor. That was the lowest common ancestor they are saying. All could be our ancestors. You can see for node 3 and 4 5, these all can be our ancestor. 4, 2 and 6, these all can be our ancestor, because with these nodes only we can reach 2, 3 and 5. But in this question they are asking about the lowest common ancestor. So the first node which is adding these two nodes can be our LCA. So that's why you can see 2 comma 8 in this case, the first node which is adding 2 and 8, which is 6. In the case of 0 and 4, tell me which is the first node which is adding them. It's 2. So 2 would be our LCA here. In the case of 7 comma 9, who is the ancestor of these two nodes? 8. It's the 8 which is adding them first. This is the first lowest common ancestor. Okay. And there is one more scenario. If somebody is asking you about 4 and 5, if these two nodes, who are the ancestor of these two nodes, so you need to find out, you need to check here, the node itself can be ancestor in this scenario. Node itself can be ancestor here. So you can see simply for 5, definitely 4 is the ancestor, but the 4 itself is the ancestor. So that's why the first common ancestor, or first lowest common ancestor, it would be, in the case of 4 comma 5, it would be 4. Are we clear now about the LCA part, guys? The lowest common ancestor. Suraj, understood now? Four comma five, not so four in the 4 comma 5. How many nodes we have? Two nodes, 4 and 5. So for the 5, the ancestor is 4. What is the definition of the LCAs? What's the definition of LCAs? The first common node, the first node which is common between both of the nodes. So for 4 and 5, for 4 comma 5, 4 is already common. It's already in the 4, it's already in the 5. That's why 4 is the answer there. So you're saying 2 is common. But before 2, 4 is the common, right? 5 is reaching to 4. 4 and 5 are not combining together to 2. Before 2, before 2, 4 is the one which is common in both. Yeah, Suraj? 4 is the common in both. So that's why 4, no, not a problem, not a problem. So 4 would be the ancestor in that scenario. Now, are we clear about the LCA part? Joseph, Deepak, Manoj, Navneet. We have already discussed this thing in earlier class as well. Got it? Okay. Now let's try to solve this problem. Now let's try to think about the solution here. Now we have understood the problem, and we have also understood the problem, right? That they will provide us two different nodes, and they will ask us the LCA for it. Correct? So first let's look into the problem also very quickly. You can see in this problem 6 to 8, they are asking about the ancestor LCA for 2 and 8. So you can see for 2 and 8, the first common node between them is 6. So that's why our answer is 6 here. Correct? Now let's look into another example also if we have. In the same example, they are also asking about 2 and 4. 2 and 4. So for 2 and 4, the first common ancestor is 2 only. So that's why our answer is 2 here. Right? So everyone understood the question? Now we can go look for the solution here. Correct? Yes. Okay. Now let's look for the solution, guys. So they are giving us two values. For them, they are asking the ancestor. So right, like now I can say that the p value, like these are the two variables which have the values. Like in the first case, 2 or 8, 2 comma 8, 2 comma 8. Right, guys? These are the two values. We need to find out the ancestor for them. 2 comma 8. Okay. Another thing, the very important part is here. They have given you that this tree is BST. That they have given you that this tree is BST. Does it ring? Does it ring your bell? Anything like that? Any way BST can be important here, or the BST properties can be important here. Something like that. They are telling you to find the ancestor for 2 comma 8. So first thing which should come into your mind, guys, how to find out these nodes. First you have to find out these nodes, then only you can tell the ancestor for them. Am I right or not? First you have to find out these nodes. If somebody is saying to you, give me the LCA for 3 and 5, so you have to first find out these nodes. Am I right or not, guys? Then only you can tell the ancestor for them. Yes. So now for finding out any element in the BST, you guys already know that because BST follow some specific properties, is that all the smaller element will be on the left side, all the greater elements will be on the right side of the root node. Right? So that's why before like while traversing our binary search tree, we will first check for the value which they are asking. Does it exist on the left side or does it exist on the right side? Correct, guys? First we need to check the value of P and Q. It exists on which side? It exists on which side? If it does not exist on any of the side, where it will exist then? If the value of P and Q they are asking, if it does not exist left side, does not exist on the right side, where it will exist? You guys tell me the answer. In the root. Yes. So now our root will be our answer there. Root would be our ancestor. You can see, guys, for the 2 and 8, you can see 2 and 8. So both 2 and 8, does it exist on the left side? Can 2 and 8 exist on the left side? In this binary tree, in this binary search tree, can you guys tell me, can 2 and 8 exist on the left side? Because it's a binary search tree and our root node is 6. Our root node is 6. 2 and 8 together cannot exist on the left side, because it will not fulfill our BST properties. And same goes for the right side as well. The 2 and 8 cannot exist on the right side as well. So that's why you can see, guys, for this 2 and 8, our answer is going to be 6. Now let's look for 7, 9. Now P dot value is 7, Q dot value is 9. We'll look for this one. But before that, you guys tell me, did you understood this part or not? Because BST is helping here. BST is helping here. Otherwise, if you remember in the binary tree, we have also done the in the LCA for the binary tree as well. That was different. But here in the BST, it is helping us. Guys, any doubt here for the first part? No? Because we can check that. We just need to check the P and Q values. If they exist on the left side, we will go into the left side. If they exist on the right side, we'll go into the right side. If they do not exist, if the both value does not exist on any of the side, we'll go. That means our root is our answer. Okay. Now let's look for 3 and 9. Now let's look for 3 and 9. Sorry, 7 and 9. Now let's look for 7 and 9. Okay. We'll start again from the root. We'll again start from the root. Okay. Does P and Q values exist on the left side? Can they exist on the left side? You guys tell me in the chat. Can they exist on the left side? The value of P and Q, can they exist on the left side? No, right? Because if they are existing on the left side, it means they are not following the BST properties. Because our root node is 6. Our root node is 6. And the value which we are looking, which is 7 and 9, it means they have to be on the right side. Correct, guys? They have to be on the right side. So now, if that is the case, we will go into the right side. We will go into the right side. Okay. Hello, everyone. Hello, Rahul. Oh, it's too late, actually. You are joining too late. That's fine. That's fine. Okay, so let's continue our discussion. I think you can just catch it in the middle, and then we can understand the next question. Okay. Yeah. So guys, so yes, so we were looking for 7 and 9. Correct, guys? So 7 and 9 are going to exist on the right side because according to BST, the root, all the greater value will exist on the right side. Am I right, guys? So 7 and 9 cannot exist on the left side and they are going to exist on the right side. And if that is the case, we are going to look for the right side now. So now we are going to this element. The next step, we are going to the right side. We are not going to the left side. Now we'll again in the node 8. We are again at the node 8. Again, we'll check the same thing. The value of P and Q exists on the left side. If our root node is 8, can P and Q exist on the left side together? Can P and Q exist on the left side of 8? But sir, we have to find LCA. How can we confirm root for 2 and 6? How can we confirm root for 2 and 6? For root and for that where we have to find out 2, 6, the root will be your answer. Again, root will be your answer. For 2 and 6. So by the way, let's wait here. Let's first understand. First, let's clear the Joseph doubt. Otherwise, he cannot understand further. If you have any doubts in your mind, you cannot understand further. So first, understand for 2 and 6. So Joseph, in the case of 2 and 6, how will they look like? They will look like this, right? They will look like this, right, Joseph? According to BST, 6 should always be greater and 2 should be on the left side, right? So again, you can check the same condition. And they will be asking like this: P val is 2 and Q val is 6, right? They will be asking like that. So 2 and 6 cannot exist on the left side together. They cannot exist on the right side together. Again, 6 will be our answer. The root will be our answer. Understood, Joseph? The root will be your answer. How can we know 2 and 8 are on same level? How can we know 2 and are on same level? Same side. You mean same side, right? Right, Joseph? You are telling that how can we know that 2 and 8 are on same side? So you will compare it. You will compare it with the root node. You will simply check. your 2 and 6 should be smaller than. Your 2 and 6 should be smaller than the root node. That's how you will check. That's how you will check. According to BST, you know that always the minimum value will be on the left side. So 2 and 6 can never be on the left side. You will compare it with the root node value. Understood, Joseph? You cannot see. Very easy, right? If this is the question, 2 and 6, let's go into the same question, 2 and 6. Now, if your value is 2 and 6, you will compare it with here. You have to first you have to decide you have to go which direction. You have to go left side or right side. What you will do? You will compare p value with 6. Is it lesser than 2? Yes, it is. 2 is lesser than 6. It means there is a chance. Let's look for q value. Is it lesser than 6? No, it's not. It means 2 and 6 cannot exist on the left side. 2 and 6 cannot exist on the left side. Why are we talking about label, guys, now here? Joseph, why are we talking about the labels? We have to go into the one side to find out our answer. Right? We have to go into the one side. If p is equal to 0 and q is equal to 8, what is LCA? If p is 0 and q is 8, 6 is our LCA. P is 0 and q is 8. In this case, I think the 6 is the first node, which is going to be our LCA. Correct, Joseph? 6 would be our LCA. Clear now? Yes? Okay. Like whatever question Joseph was asking, is it clear to everyone now? Because in the case of Joseph, in the case of 0 and 8, we cannot go into any direction. The root would be our answer. Yeah, that's what the BST is helping here. If the same question is asked in the binary tree, you have to do some other things. But BST is helping us here. Okay. Okay, so we were looking for 7 and 9. So now, guys, for 7 and 9, we have reached till root node 8. Right, guys? For 7 and 9, we have reached to root node 8 because we have seen that 7 and 9 exist on the right side. Correct? So now you need to check for root node 8. Can 7 and 9 again exist on the left side? Can 7 and 9 exist on the left of 8? No. Can they exist on the right side of 8? Can they exist on the right side of it? No. It means our answer is going to be root node. So the answer would be here 8. Same goes for 4 and 5 as well. Same goes for 4 and 5 as well, guys. Same goes for this question. You will start looking from the root node. You will see 4 and 5 exist on which direction? Okay, they exist on the left direction because they both are smaller than 6. It means they exist on the left side. Now the next root node is coming, which is 2. Now again you have to check. 4 and 5 exist on the left side? No, they can't. Now let's look into that. 4 and 5, can they exist on the right side? Yes, they can. They can, right? So that's why you went into the right side. And now your 4 is the root here. Again, you have to check the same condition. Can 4 and 5 exist on the left side? No. Can 4 and 5 exist on the right side? No. It means 4 is your answer. It means 4 is your answer. Can everyone visualize it? Yes? Easy, right? Can everyone visualize it? Anyone here who is not able to visualize this solution? Deepak, Suraj, what do you guys think? Yes? If 4 comma 5 present, right 4 is answer. Yes. Yes, Suraj. I think we have already discussed about it, right? You have to look for the common node. You have to look for the common node. So between 4 and 5, 4 is the first common node. 4 is your answer. Suraj, if you still have any doubt, please let me know. As I cleared the doubt for Joseph, I can clear for you as well. No? Okay. If anyone does not have any doubts, we can jump into the code part and let's see this. I think we have already clear about it. How we write the logic. Yes, that's what we are going to look into that. So I think our base condition is very clear here, right? Our base condition is very clear. We need to find out. We need to find out. First, we need to. So see, our code is very clear, right? We need to check our P and Q value with our root node. We have to check our P and Q value every time with the root node. If they are existing, if both values are confirming that they can exist on the left side, you have to go into the left side. If both values are saying that they are going into the right side, you have to go into the right side. If you see that scenario where you cannot go into the left side, you cannot go into the right side, you have to return the root from there. You have to return the same node. That would be your answer. That would be the code as well. Let me show you. Yeah, this is the code, guys. The lowest common ancestor. First, you fetch out the value from the, because if you will see down, we are passing whole node. So that's why we are fetching out the values. Otherwise, you can take it as an integer as well. So p dot value, q dot value. Then we are taking out a root, current node. Then we're taking out the current node value as well. Then you can simply checking. If current value is less than p val, current value is less than q val, it means we have to go to the right side. Because p val and q val, value of p and q both are greater. It means they have to go into the right side. If that condition passes, you will make your next right node as your current node, next right node as a current node. And if that is not passing, also check for the left side, if it can exist in the left side. So p value and q value, if both are greater than the current value, it means yes, it can go into the left side. Then go into the left side, make your left side node as a current node. And if both does not exist, simply return the current node. That would be our answer. Very easy code, right? Because BST has make it easy. With the help of BST, we had made this solution very easy. Am I right, guys? You can see how easily we are going into the right side, how easily we are going to the left side. And every time we are checking our conditions, we can do the similar thing in recursion as well, guys. It's just the iterative approach. We can do the similar thing in the recursion as well. Now let me come back to the chat and let me see if you guys are stuck in any of the line, any line number. Okay, so you guys are still seeing it. Okay, I will wait for one or two more minutes, and then I will come back again to the chat. Yeah, you can see we are taking the values from the node p dot val, q dot val. Then we are taking our just one variable to point out our root. Then we have taken the value from the root node, comparing the values. If both values are greater, if current node value is means current root value is smaller than the p value, smaller than the q value, it means it has to go into the right side. So make our current node as current node dot right. If current value is greater than the p value and q value as well, it has to go into the left side. Do that. If both conditions fail, simply return the current node. That would be our answer. Okay. Now coming back to our chat again. Let me see if any line. Can we try run a test case? Yes, definitely. Because let me run the code. You can see, guys, this is the BST which we have. You can see 8, 3, 10, 1, 6, 14. That's how we are inserting it here. 8, 3, 10, 1, 6, 14. And that's how it looks like. So now you can see we are passing a root node. We are passing a node 3. You can see node 3 and node 10. So what should be the root? What should be the root in the case of 3, 10? What should be the LCA, sorry? In the case of 3, 10, guys, what should be the LCA here? Let me come back to the chat. It should be 8, right? And which is our root node. Okay, I will run it. Let's look for node 10 and 14. In the case of 10 and 14, what should be the LCA here, guys? In case of 10, 14, what should be the LCA here? 10, right? So let's run it. Let's check. That's what we are comparing, see, with the node 10. So both should return true. So let's see, is it there or not? Searching, find LCA. Yeah, both are returning true. It means our code is running correctly. Now let's quickly look into this one. So now we can see, guys, I have passed node 3 and node 10, right? So now this P will be node 3, right? This value would be 3, this value would be 10, right, guys? And root would be 8. Correct, guys? Root would be 8. So now we have passed these three values, right, guys? Till now we are good. Okay, now let's look into our condition. So current node, yes, current node exists. Okay, what is the current node value? Which would be 8, right? Now we are checking the condition. Is current value is less than P value? Okay, so what is the P value? 3. Is 3 greater than 8? It would be 3, right? It would be current value. Is 3 greater than 8? No. This is definitely failing here. Correct, guys? Line number 37 is failing. Line number 37 is failing, right? Okay, now let's go into the else if case. Is the current value greater than P value? Yes, it is. You can see current value is 8 and P value is 3. P value is 3. Yes, this one is passing. Let's go for the next part of it. So current value is greater than Q value as well. So let's see that. So current value is 8 and Q value is 10. Is it greater? No, right? It's not greater, right? The current value is not greater than the Q value. So that's why, guys, if condition and else if condition both will fail here, and we will be jumping into the last condition, which is our else part, right? And we will simply return our current node. And our what is our current node? Which is 8. So that's why, guys, our answer would be the bst.root. Yeah, are we good with that, guys? Now let's look into the second use case as well, and we will dry run that as well. Okay, let's go for the second one. Oh, okay, you guys want break? So how much we spent? Oh yeah, we have spent 2 hours, I think. Huh. Oh, it was interesting, right? So that's why. So you guys want me to first explain the second one, then go for break? Ah, that's fine. Yeah, so let's quickly go through the second one as well, and then we'll go for the break. Okay. So the second use case is 10 and 14. So now the P value has become 10 and Q value has become 14. And our current node is still 8. Right, guys? Current node is still 8. Now let's further. Again, current node value is 8. Let's compare it. So current value is 8. Is it less than P value? No. Current value less than Q value? No. Because current value is 8 and P value is 10 and 14. So it will not go into this side. Correct, guys? It will not go into the line number 37. Let's look for the next if condition. So current value, which is 8. Oh, wait. Oh, I missed it. See, guys, no. That's right? P value was greater and Q value was greater. Oh, I missed it. Guys, I missed it. See, P value was 10 here, right? P value was 10 here. Oh, P value was 10 here. And Q value was 14 here. And current value is 8. Yes, it is matching, right? It is matching. Yeah, first condition will pass. This time first condition will pass. Okay. Okay, everyone can see that why the first condition will pass. I just went to the next condition, but yes, first condition will pass. Everyone can see that. Please give me thumbs up here so I can understand. Yeah. Okay. So now let's go into the first condition. What is saying? Current node is equal to current node dot write. What is the current node write? Which is 10. Correct, guys? Current node is 8. You can see current node is 8. What is the write of it? Which is 10. So now we'll update our current to 10. Now this current node will become 10. Current node will become 10. Correct, guys? Again, check the same condition. Is current value Less than p value? Yes, it is. You can see current value is 10 and p value is also 10. No, it is not less than. It is not less than. Right, guys? 10 less than 10, it's not. So it means it will go into the second part here. Okay, let's check that. Is current value greater than the p value? It's again not. It's again not. It's equal. So again, it will come into this part and we'll simply return 10 from here. We'll simply return 10 as answer. That's why you can see note 10 is our answer. That's why the LCO of 10, 14 would be 10. Are we good here, guys? Now we have done the dry run as well. Yes, because BST has helped this question a lot and made it easy. Yes, then it returned tens. Yes. Are we good with this, guys? Okay, now we will go for the break and we will all be back at 12:15. And then we'll see the next question is more interesting than this. I'm telling you guys, next question is more interesting than this. Okay, so let's join back at 12:15 and let's solve that one as well. Okay, guys. Okay. Is everyone back? Let me know, guys. You guys can hear me or not? Okay, Hariharan says yes. What about others? What about others? Can you guys hear me? So Hariharan says yes. So definitely you guys can hear me. So is everyone back? What about others? If you guys are back, please write in the chat so I can jump into the next question, guys. Suraj says back. Deepak says yes, he is also back. Okay, I think we are good to go now for the next question. Okay. I just want like if somebody is missing, then he will come into middle and then we have to repeat everything again. So that's why I'm just waiting for one more minute and then we will start. Now let's, I think we are done. So now we have done the waiting. Now we can, yeah, now we can start the next question, guys. Okay. Okay. Now this is the question, guys, which is very interesting. I think we have already done it, but let's, if not, if we have already done it, we'll revise it. If we have not done it, we'll do it. So you have been given one array and that array is rotated sorted array. Okay, that array is rotated sorted array and you have to find out any number into that rotated sorted array. So like they will give you one target number, like you will see this example 4567012 and they are saying it, this is a rotated sorted array, and I will tell you what is the meaning of subarray. Before that, in this rotated index of that element, you just need to find out the index of that element and give us the answer. Correct, guys? That's what simple question is. You have been given a rotated subarray, rotated sorted array, and you just need to tell us what is the index of that element which you are looking for. So if we do not think about, if we think about it, think this about a very simple array, and if we go with the linear approach, how much time complexity will take to find out any element in a simple array? We're not thinking about sorted, we're not thinking about the rotated. If we want to simply find out any element in the array, so how much time complexity will take? O of n. Everyone agrees with that? O of n it will take, right? So O of n, yes, O of n. So if the array is sorted, if just the array is sorted, how much time complexity now it will take to find out any element? If array is just sorted, how much time complexity it will take to find out any element? Joseph says O of 1. What about others? O of log n. Yes, O of log n using binary search. O of 1, how, Joseph? We found one, any element in the array, in the sorted array. We can't, right? We can only find out min and max in a sorted array in O of 1, but we can't. Not understood now? O of log n using binary search. Right, guys? So now for this question also, we are going to use, we somehow needs log n complexity. We somehow needs log n complexity here as well to find out any element in the sorted array. But the complexity is here. They are saying it's not simply sorted array, it's a rotated sorted array. What they are saying, it is rotated, it is rotated sorted array. Okay, so now we need to find out an element in the rotated sorted array. Yeah. Joseph, the question is, we have got the rotated sorted array and we need to find any element from there. We just need to return the element from there. You can see this is a rotated sorted array 4 5 6 7 0 comma 1 comma 2, and you got the target as 0. You need to return the index of that target, and you can see 0 exists here, the index is here. Yeah, that is our question. But we need to do this thing in a log n complexity. We need to do this. We need to do this searching in log n complexity. But log n we can only use in the sorted array, right? We can simply apply in the sorted array. But here they are asking in the rotated sorted array. So before that, guys, let's understand what is the meaning of rotated sorted array. What is the meaning of rotated sorted array? Okay. So you can see, before passing the array to us, number is possibly rotated an unknown pivot index, which is k. Like they are saying that if this is a sorted array 1 2 3 4 5 6, if this is a sorted array, so before passing this sorted array to us, they have taken one random pivot 3, and this particular array has been rotated in that values, with that value. So it means 1 would be at this place after 3 index, 2 would be at this place, 3 would be at this place, 6 would be at the I would say at this place, 5 as it at this place, and 4 is at this place. So this is, guys, your rotated sorted array, which has been rotated sorted array, which has been rotated with unknown pivot index. You can see this one is sorted like rotated like this. You can see this has been rotated like this, the unknown pivot index, and then they have given this to us. Then they are giving it's and find out any element 2. Find out element 2. So what is the index there for element 2? 0 1 2. Our answer is 4. But you need to do this in log n, not in n. Which is this rotated sorted array, not this index value. This is unknown to us, and they have given element to us. Voice is stuck. Okay, let me refresh it. What about now? Is it still same? Fine. So guys, understood the question? They have given one rotated sorted array. They have given one target to us, and then they are saying that you need to find out that target exists in the rotated sorted array or not. If exists, return the index. If not exists, return -1. And we have to do the searching part in log n complexity. But before that, did you guys understood the rotated? What is the meaning of rotated sorted array? With an unknown pivot with an unknown pivot, they have just rotated that array. You can see this is the rotated sorted array, Deepak. 4, 5, 6, comma 1, comma 3, 1, comma 2, comma 3. It looks like it has become one parabola again. It looks like it has become parabola, or not parabola, but yeah, opposite parabola, something like this. Opposite parabola. What do you guys say? This rotated sorted array has become the opposite parabola. Opposite parabola. The last question which we did, right? In the last question, we also done like we have given the parabolic equation, which was doing, which was also we have given the sorted array, but somehow with the equation we got some parabolic value, and here in the same they have with that has become up like opposite parabola. The opposite parabola, not the maximum one. It's not the maximum step. You can see it's not maximum. In middle, we are getting a smaller value. But not every time the frequency. Yes, every time frequency is going to be same. Every element we rotate the same. So Deepak, every element in the array will be rotated with the same value, same pivot index. That would be 3. 3 or 2. Ah, okay, you mean not the same. Yeah, that's right. Any unknown value could be there for k. That's totally right. That's totally right. Any value can be there. 3 or 2, 0, anything like that. Okay, guys. Understood rotated sub-array, rotated sorted array. Sorted array, everyone understood? Guys, can you write in the chat? Did you guys understood? Yes. What about us? Navneet, Kumar, taking it, guys. So please tell me. Okay. So now, okay. So now let's think about it, guys. How can we solve this question? Because we need to do it with the help of binary search. Or again, happening to everyone. Or you guys can also try to. Okay, today I'm not sure what happened with my internet. Internet is having some problem here. And actually, internet problem has started 1 minute. What about now, guys? Is it fine now? Yeah. Okay, so as I was saying, we need to do the solution here in log n time. In log n time, so we can only do the log n with the help of binary search, right? With the help of binary search. Am I right, guys? With the help of binary search, we can do in the O of log n, right, guys? Okay, so in the binary search, if you guys remember, in the binary search, we should be knowing, so our array should be sorted. It means in the binary search, we should be knowing from where to where it is incrementing. Because see, this is sorted array, right? If we take the same array, 4, 5, 6, this one, 4, 5, 6, 1, 2, 3. If we take this array, and if we are looking for 2, so we should be knowing that, we should be like aware of, we need to look into this part, because 2 is at the right side, not to this side. Correct, guys? We should be looking into the right side, not into the left side. Right, guys? Then only we can get the answer here. Correct, guys? So guys, for doing that, we should somehow know here that from where our array is starting. From where our array is starting, or how much or how much our array has been rotated. Because if we somehow know that the value of k is 3, we would be we would be sure that the first index would be at the 3th. The first value or the like array is starting from this index. Correct, guys? Yes. So we are going to find out the minimum here. We are going to find out the minimum here. And guys, let me just tell you, finding minimum. Repeat last part. Okay, first let me repeat the last part again, so Suraj can also understand the next part as well. So Suraj, what I'm saying, for finding out, because for applying our binary tree, we should be knowing first. We should be knowing from where our array is starting, from where our sorted array is starting. So for that, we need to find out the minimum element in our array. We have to find out the minimum element in the array. Right, guys? Because we only after that, once we find out the minimum element, what we'll do, we'll say that after this element, after this, there is one part where you can check the answer, or after this there is another part where you can check the answer. Because after the mid element, we can say that like we can say that what we can say that the value, the target which we are looking, it might be on the this side, or it might be on the this side. It can be on the any of the side. Correct, guys? So that's why we need to find the minimum element first in the rotated sorted rotated sorted array. Then only we can understand the search space for our binary. Because in the binary search, if you guys remember, in the binary search, we cannot directly, why we cannot directly apply the binary search in this? Because in the binary search, we first find out the mid element. Then we look for, if the value which we are looking, if it is less than, the mid, then we have to go to the left side. And if it is greater than the mid, we have to look for the right side. That's what we do in the binary search. Based on the mid and our target, we decide which side to go. Yes, but here we can't directly apply, because if somehow 6 is coming, you can see 6. If the target is lesser than 6, we might can go onto the this side as well. We might go into this side as well, because you can see both side we have the minimum values. Both side we have the minimum value. That's why we cannot decide here. Which direction to go. So for that, we should be knowing from where our sorted array is starting. So for that, guys, we are going to find out first in this array minimum element. Okay, everyone understood why we are going to find out the minimum element here? Anyone has any doubt? Okay, now let me just give you one more important thing here. Once again, which part? We are going to find out the minimum element in this rotated sorted array, just because of we want to know from where our sorted array is starting. From where our sorted array is starting, because that will help us to apply the binary search logic. Because binary search logic can be only applied in monotonic stack, right? Monotonic values. It should be incremented or it should be decremented. We can't apply binary search in any of the arrays which are like like this, where where we cannot decide which direction to go. Yes, where we cannot decide which direction to go. Right, Arat? We are trying to find out the minimum element. So from where we can understand that right side of it is going to be greater, left side of it is going to be smaller. We can see that, right? Somehow find out the element 1, we can say that all the greater element will be on this side. Like some greater element will be on this side, and some greater element on this side. Right? So last would be min I minus 1 for binary search. Yes, correct. Yes, yes, definitely. So we will get two binary search, two here things. See, in this array, once we find out the minimum element, so this would be our minimum element. So then we will do searching in, this is our start, this would be our end. Then we'll do searching. First we'll apply binary search into this one. So start, comma, min minus 1. This is the first part of search. The second search would be min, comma, end. Now you can see, guys, we got the incremented values. Now we can apply simply, these are the sorted values. Now we can simply apply our binary search in both of them and find out our final answer. That's why, guys, we are trying to find out the minimum element. And after that, we'll simply apply once we find out the minimum element, we'll simply apply the binary logic because we have the correct indexes now. You can see till here we got the first end, which are the incremented value. Some value could be here, value could be here. Understood, guys? Why we are trying to find out the minimum element here? So we can get the two search space. And then we can simply apply the binary search logic into that. Everyone understood? Anyone has still doubt? Let me know. Then we can move into the next part where how to find out the minimum element. Please let me know. You can just thumbs up here so I can go into the next part. Clear? Okay, clear for Suraj as well, for Joseph as well. Okay, now it is clear, right? So now let's go back to understand how to find out the minimum element. Okay, now guys, for finding out the minimum element, there are only three cases. There are going to be only three cases. Let me show you. So first case, guys, left and right. So the case one, guys, can we say that this is rotated sorted array or not? Can you tell me this is the rotated sorted array or not? Okay, everyone says no. Anyone says yes? So it is a rotated sorted array. It is a rotated sorted array, but here k value is 0. That's why it is not rotated at all. Got it, guy? Got it, guys? It is a rotated sorted array, but here the rotated value is 0. Oh yes, the second one also Arada said correctly. If we rotate it 7 times. Yes, if it is rotated by 7 times. Yes. That's also right. If we rotate it with the array dot length. That's totally right. Arad. Yes. Got it, guys? This is a rotated sorted array. Everyone agrees? Anyone has any doubt into that? Okay. In this case, how to find out the minimum element? So your first case is when your left is smaller than right, leftmost, when your leftmost is smaller than rightmost, so your left is always minimum. Left is always minimum. You can check, guys, any of the scenarios. This is the fact. In the rotated sorted array, if your leftmost is smaller than the rightmost, the array is definitely going to be always sorted. This is the case 1. K is the pivot index. K is the pivot index which is helping us to rotate the array, which is helping us to tell us this is, and that value is unknown here. That value is unknown here, which we do not know. That value could be anything. That's not given in the question. Unknown pivot means some values with that, with the help of that values, we are just rotating our arrays and we are not sure about what is that value is. Okay, that is K here. Okay, so now guys, this was the case 1. Now case 2. Case 2, which we can take from here only, this one. 4, 5, 6, 1, 2, 3. Again, your leftmost, your rightmost, and then your mid. Find out the mid here. So what would be the mid here? 0, 1, 2, 3, 4, 5. So what would be the mid here? 5 divided by 2. 1 minute. 1 minute, guys. Just give me 1 minute, guys. Huh? Yeah, okay. So what would be the mid here? So in this case, our mid would be 2, right? So this would be our mid. So now we need to check, guys, if our mid element, is smaller, if our mid element is smaller than the right side, if our mid element is greater or smaller than the right side, because you can see, you can check for the right side or left side, any side you can check. But right now I'm going with the right side. So if my mid element is greater than the right side, then definitely minimum is going to be into the right side. Then definitely minimum is going to be in the right side. Am I right or not, guys? If my mid element, is greater than the rightmost, if my, just listen these words, if my mid element, this is the mid element, if it is greater than the rightmost, definitely minimum is going to be on the right side. Yes or not? Definitely minimum is going into the right side, right? Everyone agree? Yeah. So now in this case, what we'll do? We need to increase our left to here, into the mid part. We need to increase our left to here. So we'll increase our left to left plus 1. Simply left plus 1. Now our left is here. Now again, do the same thing. What would be the mid here, guys? What would be the mid here? So this part, right? Right, guys? That would be our mid. That would be our mid. Now again, check the same condition. Is our mid greater than the right? Is our mid greater than the right? No, it is not. It is not. So what we'll do in this case, definitely our minimum is on left side. Definitely our minimum is going into the left side. Correct, guys? Definitely our minimum is going into the left side. So now in this case, we will reduce our search space for right to here, to mid only, to this element, because 2 could also be in the answer. Now guys, you can again find it out, left and right. You can see here, left, the case 1, left has become less than the right. Left has become less than the, oh, by the way, wait. Oh, by the way, see, no, guys, you do not need to go this scenario. When we have moved it first time, by the way, I forget the case 1. When I was in this scenario, when I moved my left here, you can see left has automatically become smaller than the right. Left has the case 1. Left has already become the smaller than the right. I think here we can see the answer directly there only. Left is always our answer. We need to go again. No need to go again. Answer is 1 here. You can see, guys, case 2 already here. In the case 2, case 1 has already been there. We don't need to go further. Got it, guys? The case 1 was already there. So guys, that's why there are 3 cases only. There are 3 cases only. So the first case, if your leftmost is smaller than the rightmost, if your leftmost is smaller than the rightmost, always you have to return the leftmost. Almost you have to return for the leftmost. But we will not go to 2 less than 3. Will not go to 2 less than 3, right? We have not gone to 2 less than 3, right? You can see I was here only, right? I was checking with 1 less than 3. I have not gone to 2 less than 3. Understood, Joseph? I have not gone to 2 less than 3. Okay, so there are only 3 cases, guys. First case, if your leftmost is smaller than rightmost, if your leftmost is smaller than the rightmost, just return the leftmost. That is our minimum element. Okay, if that is not the case, then the second case, if your mid element, if your mid element is greater than the rightmost element, if your mid element, you can see here when we were at the 6, if your mid element is greater than the rightmost element, go into the right side, increase your left to mid plus 1. Now this will be your search. Okay, and if else, if this is not also not the case, if your mid element is not greater than, the rightmost, it means it's smaller than the rightmost element. In that case, you need to go into the left side. Definitely into the left side there is a minimum. If your mid element is already smaller, like this, like in this scenario, guys, 4 4, 5, 1, 2, 3. Yeah, in this course. No, not in this question also. 1 minute. 2, 3. 1 minute. Yeah, not in this question. But yeah, if we have like this 5, 6, 1, 2, 3, 4. Yeah, in this question. Right. Yeah, in this question. What would be the mid here, guys? What would be the mid here? Oh, no. In this question also, it's not working. 1 minute. Let me create the example for that. Our mid should be smaller than the rightmost. One minute. Let's increase one more element here. The 5. If I increase 5 here, 1 minute, guys. And if I increase 7 here, what will happen here now? 6, 7. Yeah, 6, 7. What will happen now? 0, 1, 2, 3, 4, 5, 6. Yeah, 0, 1, 2, 3. Yes. You can see. Yeah, guys. Yeah, this is the example. So now you can see our mid is this 0, 1, 2, 3, right? Mid would be 3 right here. So mid would be this. Now you can check your mid. Is it greater than the rightmost? No, it is not. It is smaller. It means your minimum is going to be on this side. This is case 3. Your minimum is going on to this side. So you have to go into the left side. You have to make this right to here, because 2 could also be the answer. And this is again your left. Understood? These three cases are easy, right? The first case, if your leftmost is smaller than the rightmost, you have to return the leftmost. That is your answer directly. But if that is not the case, then there are 2 more cases. And 2 more cases are, you have to first find out the mid element. You need to check with the rightmost. If your mid element is greater than the rightmost, if it is greater than the rightmost, you have to go into the right side. And if your mid element is smaller than the rightmost, you have to go into the left side. That's what the 3 cases are. Understood, guys? Those were the 3 cases. Understood, Joseph? Now all 3 cases, these only 3 cases will be there. There will not be any other cases in your rotated sorted array. These are the 3 cases which you can see in the UI as well. I have written the example for every cases. This is the example 1. This is the example 2 for case 2. And this is the example 3. Where you can see, in this case, your leftmost is smallest than the rightmost. You can see you're simply written, your left is minimum. In this case, your mid element, which is this, which was greater than the rightmost. Then that's what you can see, minimum was at the right side. In this case, your mid element, which is this, was smaller than the rightmost element. Then your minimum is going to be on the left side. That's why you can see one is at this side. Yeah, just like binary search, yes. But yeah, smartly, here we are using the smart brain, our brains in the rotated subarrays, rotated sorted array. Everyone understood how to find out the mid and max, how to find out the minimum element? All three cases, everyone understood? Yes? And this is the question actually has been asked in the Amazon, Google, and bigger companies, guys. You can check in the internet as well. Finding out the minimum element, finding out the minimum element in the rotated sorted array. This is the question has been asking. That's why I was saying this was an interesting question. Okay. Now, first let me show you the code for this, guys. Directly for the finding out the minimum element. Because this is separate question. Let me show you direct the code for this. Okay. First, yeah, before that, anyone has any doubt till now? Anyone has any doubt? Hariharan says no. What about others? Aras says no. Deepak says no. Navneet says no. Suraj also says no. What about you, Joseph? Are we good there? Which is smart approach? All which case you didn't understand? Case 1, case 2, case 3. Case 1 was very right. Case 1 you didn't understand. First case. See, the case 1 was this, right? When your leftmost element is smaller than the rightmost element, you have to simply return you do not need to find out any mid element, anything like that. You can simply return the answer from there. That leftmost is going to be minimum. This is the case 1. You do not need to find out any mid element there. Case 2. In case 2, when you see that this is not the scenario, when you're leftmost, you can see, first always you will check the first case. When you see that it is not passing, you will go into the case 2. There what you will do, first you will find out the mid element. After finding out the mid element, you will check that your mid element, is it greater than the rightmost element? If it is greater than the rightmost element, definitely minimum is going to lie on the right side. You will again, you will update your left pointer to mid plus 1 and right will still be there. And then again you will do the same thing. Correct? That was the case 2. Understood, Joseph? That's case 2 as well. When you are not able to solve your question with the first case, you will go for the case 2. In case 2, you will find out the mid element. You will check that is that mid element is greater than the rightmost. And if it is greater than the right side, your answer, your minimum element is going to lie on the side. So what you will do, you will update your left pointer to plus. The case 3 is if your mid element is not greater than the rightmost side. If it is not greater than, then your answer is going to lie on the left side. You will update your end pointer this time. Your right pointer to mid. You will do the left and right here. Yeah, again then find. Again for the next element, you will again first go for the first rule. You will again go for the first rule. And you will check there. Okay. So now let me show you the code, guys. Now let me show you the code. Let me bring this case also inside it, guys. No minute, yeah. Bring this also here. Return left. Yeah. This is case 1, guys. You can see. Okay. By the way, let's start from there. Find minimum index. They have passed you the rotated sorted array. You have taken left as 0, right as the last element. Last element. Correct. Last element index means last element index. Rotated sorted array length -1. So you can see this is 0. And if I take the same example, this one 4 5 6 1 2 3. If I take this one 4 5 6 1 2 3. 4, 5, 6, 1, 2, 3. In this array, you need to find out the minimum element. So left would be 0. So right would be 0, 1, 2, 3, 4, 5. Correct, guys? right would be 5. Correct? Right would be 5. Now let's move further. If rotated sorted array length is equal to 1, if we only have one element into this, like this, it means this is only going to be the minimum element. That's why we are returning the left index. Minimum index is 0, but this is not the case which we are tackling right. So now let's look for the while this one. While left, we keep this, so we can look here. Yeah. So now you can see left, yes, left is 0 and right is 5. So yes, it is. Now we'll check that. Is the rotated sorted array left most is less than right most? No. You can see 4 is less than 3. 4 is less than 3. No, right? 4 is greater than 3. So that's why this condition will fail. This condition will fail. So case 1 has been failed. Now we go for the case 2. So before that, we will find out the mid element. You can see, I find it out the mid element. Then I am checking, is my mid element greater than the rightmost element? If yes, then increase our left pointer to mid plus 1. So let's see in this case. So our mid element would be 6. Right, guys? Mid element would be 6. And then is that 6 greater than the 3? Yes, it is. So now our left will be updated to, now our left would be updated to, right now left is 0. Now left will become 0, 1, 2, and 3. So now left will become 3 here. Right, guys? Now left will become 3. And you can see the else scenario as well. This is the case 3. If your mid is not greater than the rightmost element, you have to bring your right pointer to mid and you have to sort the search array. And you can see in this kind of scenario, now 3 will be left. Left will be 3. Right is still 5. We'll again check. Is the leftmost element smaller than the rightmost? Yes, it is. Simply return the third index. And that's why here our answer would be third index. Third index is the minimum one. Just see that, guys. Just see this. Because this is the question has been asked in the Amazon, Google, that this much part only. Find out the minimum index in the rotated sorted array. I will wait here, guys, because this is the important part in this question, not the remaining one. Did you guys understood now? Coding as well, how we are doing it? Anyone has any doubt? Find the minimum index in rotated sorted array. Anyone has any doubt, any line where you guys are stuck or not able to think about what this line is doing? Are we good, guys? Can we move into the next part? So for now we have find good, right? Arad, what about you? Arad, Suraj, what about you guys? Are we good here? Yes, good. Okay. So now we have find out the mid element. Now, sorry, minimum index. Now we have find out the minimum index. So what is the next step? Once we find out the minimum index, we just need to put this thing start to min minus 1, min to end. That's what, guys, we did. Now let's start looking into our question from the starting. So this is the search method where you can see I'm passing my array. I'm passing the target which I'm looking here. So first I find it out the minimum index. Once I find out the minimum index, you can see I'm passing my whole array, target, and then 0 to min index minus 1. And then min index to nums dot length minus 1. You can see left and right. Whatever value which I'm getting max from there, we'll simply taking it up. And you can see the binary search as well, which is very simple. The binary search which we have done earlier. Look for if mid is equal to target, return the mid from there. If mid is less than target, increase your left. If mid is greater than target, look for your right side. And if you're not able to find out that target, just return the minus 1. So that's why, guys, minimum index has helped us to reduce our search space. That's why you can see how the minimum index is helping us. You can see once we find out the minimum index for this question, this was the minimum index. Now we know that this is the one search space. This is the one search space. And then we simply started putting our binary, because now we can simply put our binary search logic here. The same older binary search logic here. Find out the mid element, check that if it is matching with target. If not, reduce your search space. So the first part of the question, which was the finding the min index, that was important here. And that's what has been asked in bigger organizations as well, like in the Amazon, Google, or everywhere. Yeah. And meanwhile, let me open the code for you guys so you guys can see it. I think yeah. After that, there is nothing. Find out the minimum index. Once we find it out, we just broken our search into two parts: finding out the left part, finding out the right part. Anywhere that element can exist. But now with the help of binary search, we can simply search it out within the login complexity. We do not need to go for the end this time. And then whichever is greater, because you see, if we do not find it on the right side, we will be like, if we talk about this example, if we find trying to find out 2 here, so we will not get it from the left side. So left side will return -1, and from the right side we will be getting this index, whatever that index is, 0 1 2 3 4 4 index. So we'll simply return 4 from here, because from the left side we will be getting -1, from the right side we will, from this left will be returning as -1, and this right will be returning as 4 from here, from this method. Then the max of it would be 4. We'll simply bring the 4 as our answer. Understood, guys? Yeah, login only. Yes, we are doing the O login. Yes, definitely. The time concept should be O of login here. So I know this question was interesting, right? Or not the whole question. The first part of this question was very much interesting, which was the finding the minimum index. That question has been asked in many of the interviews. That's why I was saying that question is interesting. Okay, guys, anyone has any doubt here? Because now we are at the end of our class for today. Are we good, guys? How are you feeling after solving these interesting questions, guys? And let me first push this all the changes in our in the GitHub so you guys can see it. I think we just added some numbers there, which if we not add, that's also fine. But yeah, let me add it. Class fix git push. Yeah. Now everything is available in the GitHub as well. And yes, somebody was asking, is it the last class? No, Suraj. We have one class on Monday as well. We have one last class on Monday, and then that would be our last class. So how you guys are feeling after doing these 5 interesting questions? Some was very easy. I think for some people, I think XOR would be new, and max depth and LCA was not new. We have already done it earlier as well. But now I think you should have proper visualization for those questions. And I think distinct element, I think you guys are already aware of object and map. And then this last question was very interesting for finding out the minimum index. Yes, definitely. Practice is needed now. Okay, guys. So yeah, last one is. So I think next class we will be solving the problems. And I think, guys, in the next class, I have seen that the similar problem we have there as well. The same problem, finding out the minimum index in the rotated sorted array. So I think we have already covered it today. So next class, no need to cover that question. Same problem we have there. Find out the minimum index in rotated sorted array. That's the question we have there, which we have already covered here. So I think in next class, we will be having some time where we can talk about something else as well. Okay. Okay, guys. So now let's wrap it and let's spend your weekends, do some practice, have a nice weekend, and we'll talk again on Monday. Okay, guys. Bye-bye.